So 6 says, the directions say find the value of the 6 trigonometric functions using identities or reference triangles. And 6 says that secant theta is equal to 1 and cosine theta is equal to undefined. Well, we have our some answers here. Of them we already have on the other two. Well, I know that cosine is equal to, so cosine should be 1, right? And then I know that sine squared theta plus cosine squared theta should equal 1. If cosine is 1, 1 squared is just 1. So sine squared should equal 0, so sine should equal. Okay with that? And then I know that tangent is sine over cosine. So that's 0 over 1, or just 0. And then I know cosecant is 1 over sine. And that's everything, right? So like 0 over 1 is equal to 0. 1 over 0 would be undefined. So if you think about it as like a division problem, like if I have 0 things and I split them one way, there's still just 0 things in that pile, right? If I take a pile that has 1 thing in it and try to split it to 0 sections, that doesn't make any sense. That's undefined, right? Because that's basically what division is. If I have like 6 divided by 2, I want to take 6 things and split them into 2 piles. If I have 0 things and want to split them into 2 piles, well, there's still 0 things in each pile. If I have like 6 things and try to split them into 0 piles, that doesn't make any sense. So that's the difference between like 0 and undefined. So denominator is undefined, numerator is just 0. Is that good? And 0 over 0 is still undefined, just FYI. So like the denominator 0 overrides the numerator 0. Victoria. Sure. So here we have tan x over cosecant squared secant. Okay. So I see the fast way to do this, but there's lots of different ways you could do this and end up at the same result. So the first thing I notice is I notice an algebra thing that I could apply here. If I look at each of these fractions, there's a greatest common factor involved here. That greatest common factor being tangent. First, okay there. And that's nice. Fractions, the 1 over cosecant and 1 over secant. I'm sorry, 1 over cosecant squared and 1 over secant squared. And I can get rid of the fraction, right? So I know 1 over cosecant is the same as sine. So 1 over cosecant squared would just be sine squared. Secant is cosine. So 1 over secant squared is cosine squared. Okay with that, Victoria? And then sine squared plus cosine squared is just 1. And 1 times tangent is just tangent. Okay there? Sure. Elizabeth? 7? Sure. So we have cotangent. Well, there's no algebra thing that sticks out here because there's not any like terms or whatever else going on. So I would probably start just by rewriting cotangent using one of the quotient identities. So cotangent is the same thing as u. And since I'm multiplying these two as fractions, I'm going to rewrite sine u as just sine u over 1. So when I'm left with cosine u over 1, or just cosine. And that's it. Is that okay? Haley? Sure. So I notice an identity thing right away that I would want to use. If I look at the numerator, notice I have a sine squared plus cosine squared. So that just becomes 1. Okay, there. And then I recognized 1 plus tangent squared as one of my Pythagorean identities. That is just secant squared. And then I can just reduce this fraction, right? And I'm left with just secant beta. Jason? Sure. So if I look at 14 that I can use here, right? So let's do an algebra thing. In order to get this simpler, I'm going to have to add these two fractions together at some point, right? Because one fraction is simpler than 2. To add these two fractions together, I would need to have a common denominator. What would the common denominator be in this case? Just going to be 1 minus sine times 1 plus sine, right? Everybody's okay with that idea? Just like when you did rational expressions last year and you had like 1 over x plus 1 plus 1 over x minus 1, and the common denominator is x plus 1 times x minus 1. Same idea here, just we have signs involved. So that's going to give me 1 plus sine y plus 1 over 1 plus sine y. Now if I look at the numerator, I can combine like terms up there. So 1 plus 1 is 2, and sine y just 0. So I just left with 2 up there. And then, well, again, there's no obvious identity that I could use on 1 plus sine y and 1 minus sine y. So let's multiply them together. Maybe we'll get something useful if we FOIL that out. That's just like a difference of 2 squares situation. So rather than doing the full foiling, I'm just going to write it as a squared minus b squared. You could FOIL the whole thing out. You'll get the same result. It's no big deal. I'm just saving time and explaining to you how I did the multiplication just so instantaneously in my head. So far, so good. And now this isn't, but it's pretty close, right? Notice that if I subtract the sine squared from both sides, that's now what I have. Everybody see that? So I'll write that as 2 over cosine squared x. And then that's really the same thing as thinking like 1 or 2 times 1 over cosine squared x. Oh, I meant all of a sudden here. Krista, are you stretching? You have a question? Okay, stretch on. Just checking. And then 1 over cosine squared is just going to be secant squared. Jason, are you happy with what we did there? Gracie? Well, I just rewrote that so it was easier to see what was going, like how I turned it into 2 times secant squared by thinking about it just like the product of 2 things rather than like, wait, what? How's that? You know what I mean? So I just wrote it that way for clarity. I didn't do anything other than just like turn it into a multiplication problem. That's all. Is that okay? Josh? Memorize the proofs? So the identities I would, like this set of identities I will give you for this test. Moving forward, these are identities that you'll end up probably memorizing just from doing the homeworks and whatnot. But these basic ones are ones that eventually I will expect you to have memorized, but not for this first test on them. Is that fair enough? So we'll take some time and let you kind of get used to them, but hopefully you end up memorizing most of them kind of along the way. Okay. Victoria, you had your hand up.
Yeah, I figured that.
Oh, okay. Any last questions from this assignment? Okay, we can always come back and ask more next time about it. Doesn't mean that you can't ever go back to it. So today, we're going to start the next section. So here we're going to be talking about solving trigonometric equations. So last section, things like find the value of sine inverse of 1/2, right? So here, we only have one answer for this because we had said that the domain of the parent or of the original function. So the output that we're going to get is going to be locked here in between negative pi over 2 and positive pi over 2. You're given a context to find an answer over some different interval. If I contrast that with if I want to solve sine theta is equal to 1/2, because if we can find one location where sine is equal to 1/2, we can just keep going coterminal and keep finding them and finding and finding them. And that's okay because a function can have lots of duplicating y values, right? We can keep getting 1/2 as a y coordinate over and over and over again, and that's not an issue. Like we can't have an input and get a bunch of different outputs, right? Which is why we had to be careful about the inverse. So here we're going to be talking kinds of problems, which are just ever so slightly different than the kinds of problems that we solved in the previous chapter, because now we can have lots and lots and lots and lots and lots and lots of answers. Okay, we're not limited to just like one inside of this specific interval. We can have many. Okay with that idea? So let's do some examples here to help kind of get used to this. So if I wanted to solve that sine of x is equal to 1/2 on the interval from 0 to 2 pi, that's equivalent to saying I want to find the value for x where x is between 0 and 2 pi, right? Like as an inequality, like it looked like last section. Now to get x, we'll do sine inverse of both sides. But now instead of being restricted to just the values between like -pi/2 and +pi/2, I can look anywhere from 0 to 2 pi. Everybody's okay with that notion? So to do this, I can, because this is a unit circle value, if I go to my unit circle and I look for places where the y coordinate is 1/2, I get an answer here at pi/6, and then I get another answer over here at 5pi/6. So now all of a sudden we can get more than one angle. Is that okay? What if, for example, we had taken away this piece? How many answers do we have here? Infinitely many, right? So how do I represent infinitely many solutions here? Well, I'm going to say I want the solution pi/6, and then anything that, and the way we say that is just say plus 2 pi k, where k is a value in the integers. So remember, the integers are your positive or negative whole numbers. So we're going to be adding or subtracting just some multiple of 2 pi, which just means we're going another time around the unit or the circle there, just either forwards or backwards, right, Elizabeth? That's a comma, and then k is a member of the integers. So that's just notation. We've used that notation before when we described like, when did we do that? When we were describing some of the key features for like tangent. I think we used that same notation where like the asymptotes were or whatever. And then similarly, we can do the same thing for the other answer, 5pi/6. We can say that and then everything coterminal to it. So this part here just means when you see that, it's just basically talking about everything coterminal to it. So for example, if k equals 1, then we have pi over 6 plus 2 pi times 1, which becomes, when we make a common denominator, it becomes like 12 pi over 6. So it'd be like 13 pi over 6 as another answer. Or if k2, we have pi over 6 plus 2 pi times 2. So 2 pi times 2 is 4 pi. When we make a common denominator with 6, that's 24 pi. And pi over 6 plus 24 pi is like 25 pi over 6. And you could keep going and doing this as long as you wanted to, right? Is everybody okay with that? I'm just trying to explain to you how that notation is representing everything that's coterminal to that initial answer, is all I'm really trying to demonstrate there. You would not necessarily really have to do that, but I'm just showing you kind of why that notation is representing infinitely many answers that are just like everything coterminal to some initial answer. Okay with that? Okay. Well, that's the basic idea. Let's just do some more examples as the solving gets a little bit more complicated. But this is the same basic idea that we're going to be doing over and over and over again. Okay? So we'll just do some examples where the algebra gets maybe a little messier to kind of get a feel for how to do this kind of thing. Okay? Okay, so let's say we want to solve cosine squared x is equal to 1 on the interval from 0 to 2 pi. So again, to solve cosine squared x is equal to 1, I want to get the x part by itself. So what would I need to do first? I'm sorry, you mumbled kind of quietly and there's a mask and I just couldn't really hear what you said. Okay, so cosine squared is an operation. That'd be like saying, oh, to solve the square root of x, I'm going to divide by square root symbol. So that doesn't really make a lot of sense. I'm not trying to embarrass you. I'm just trying to be clear as to like why that doesn't make a lot of sense to help build some intuition. So cosine squared is like an operation. So you can't undo an operation by doing like dividing by that operation, right? So if this was just like x squared is equal to 1, what would you do first? Square root both sides, right? That's what we should do first here to get rid of the squared on the cosine. Now remember, when you square root both sides of an equation, you get a plus or minus. Very easy to forget to do that. I'm sure you've forgotten many times in your mathematics careers, but we should try to make a point of remembering to do that. And now, really, we need to break this up because we can't solve something with a plus or a minus. Two equations, one where it's a positive and one where it's a negative. Is everybody okay with that idea? Now, how are we going to get rid of the cosine part? Use the inverse cosine. And now I can look anywhere on my unit circle for the places where cosine is equal to 1. So that's going to be where the x coordinate is equal to 1. So if I go and I look at my unit circle, here at 0 degrees or 0 radians, and doesn't happen again until I get to 2 pi radians, but that's not inside of the interval that I'm solving for, so I just have 0 for my answer there. My other problem, I had cosine inverse of -1, so I'm going to go look for places where the x coordinate is -1. That happens just here at pi. Is everybody okay there? Okay. So let's write those down. So those would be my two answers in between 0 and 2 pi. If I wanted any answer, I can just the or everything coterminal to it. Piece. But if you look carefully at these, we could do a little bit better. So if we think about in practical terms, we have an answer at 0, we have an answer at pi, we have an answer again at 2 pi, we'd have an answer again at 3 pi, and then 4 pi, and 5 pi. So really, how often are we encountering an answer? Every 1 pi, right? So I could really just combine these together, and instead of saying every 2 pi, and that's really the same result. Now I wouldn't mark that down or anything if you wrote it as 2 separate chunks, but I would tend to think if you're looking at a multiple choice test, they would write it as a single solution rather than 2 separate solutions in that case. Now that doesn't happen very often, a case like this where we can take our 2 infinite solutions and combine them into really just 1 solution. But it happens here and there, and I just wanted to make a point of that. But really for this question, that's our answer on that interval. If we're looking for any interval, though, that's what we would have. Or all of our answers, I guess I should say, is that's what it would look like. Okay with that idea? And we'll probably stop doing all the infinite answers here alongside after a minute, because all we're really doing is tacking on a 2 pi k at the end. This was the only situation that I think in the notes that I have written out that something weird can happen, so I just wanted to show that to you guys. Let's look at another example. So let's say we want to solve 3 tangent squared x is equal to 1 on the interval from 1 to 2 pi. So what would I want to do first? Divide by 3. Very good. And then square root both sides. Yep. So remember, when we square root both sides, we get a plus or minus. And to square root a fraction, we squared the numerator and squared the denominator. But the square root of 1 is just 1, so I just wrote it as 1 there. Is everybody okay with that? And then we'll bring okay there. Now, notice that I have a square root in the denominator here. I don't really need to worry about it because it's not going to be part of a final answer. So if you wanted to rationalize your denominator here, you're free to do that, but you don't really need to, because this is not a final answer, just some work along the way. So I'm not going to bother with it. Is that okay with you guys? Okay. And then now we can just apply our inverses. So remember, if we're going to go to our unit circle, tangent is equal to y over x. Now, I know that if I'm looking at my unit circle, there's no place where the y and the x coordinate is square root 3. But if I, say, divide the numerator and denominator by 2, which is okay to do, right? That's just like finding a common denominator thing where we multiply by 2 over 2 or whatever. We can certainly divide by 2 over 2. I do have places where the coordinates are 1/2 and square root 3 over 2 on the unit circle. So that's why I'm pointing this out, just so I see where I'm looking at the unit circle. So I'm looking for places where I have 1/2 as the y coordinate and square root 3 as the over 2 as the x coordinate. So I have one answer here at pi over 6. And the same thing could happen as if they were both negative, right? Because it's y over x. Negative over negative makes a positive. So I also get 7 pi over 6. And then similarly, if they were both, or if it was negative 1 over square root 3, it would mean one of the coordinates was negative and the other was positive. So for the other piece, I could have 5 pi over 6 or 11 pi over 6. You guys okay there with what I did? Okay. What if I have 2 cosine squared x plus cosine x plus 1? What do you notice right away that's different about this problem than any of the previous ones we've done? I'm sorry, you mumbled a little bit and I couldn't. Good, so we have x's in more than one location. Excellent. Does this remind you of anything that you've done before? Looks like a polynomial. Very good. Specifically, what kind of polynomial? Quadratic. So we can solve this basically the same way we would solve a quadratic. And just to make this extra clear, let's just say that we're going to substitute the letter A for our cosines, just to make it a little bit more obvious. So we would have like 2a squared plus a is equal to 1. Now it surely looks like a quadratic, right? How would you solve this quadratic? Good, so Josh says let's move the 1 to the other side so that it equals 0. Great. Then what? Yeah, so Josh is going to try to factor this. Factor this, we need to find two numbers that multiply to give us 2 times -1 and add to give us positive. Right? A times C. They have to multiply to give you A times C and add to give you B. Everybody remember doing that factoring last year? It's probably the single most important skill from your Algebra 3-4 class that you must remember is how to factor and solve quadratics. What are those two numbers? 2 and -1. Very good. So once we've located those two numbers, what we do is we replace that middle term with those two numbers. So instead of A, I'm going to write 2A plus -1A. Oops, still equals 0. From the first group, we can take out a greatest common factor of 2A. From the second group, we can take out a greatest common factor of -1. Look at these two terms. They both contain a factor of A plus 1. So when they factor that out, we're left with 2A minus 1. And there's our factored form. Right? You remember doing this long factoring method last year in Algebra 3-4 class? Again, I don't expect you to remember how to do it instantly, but that's part of the reason why I chose this example to make sure that we go through again, reminding you guys how to do this. Then we can apply the zero product property. So I can set each of these factors equal to 0. But remember, we're not solving for A here. We're solving for X. So let's go back and substitute back in that A was equal to cosine X. So far, so good. And then I go to my unit circle. The only location where the x-coordinate is -1 is at pi. And then if I go and I look for the locations where the x-coordinate is 1/2, that's at pi over 3 and 5 pi over 3. So those are my answers. We okay there? Okay. So let's say we want to solve sine 2x equals 1/2. How is this different than any of the problems we've seen before? We have a coefficient on the variable. Exactly right. Yeah. So that's going to make things a little bit different. And I'll worry about that here when we get to it. But we would start the same way we would in just trying to get the x by itself. So to get rid of this of both sides. And then we would go to our unit circle and look up the places where the y-coordinate is 1/2. That happens at pi over 6, as well as 5 pi over 6. And now we would think, okay, we'll just divide both sides by 2 and we're done, right? Would make sense. And I would agree those are answers. The problem is we've missed some other solutions. So the way to guarantee that we don't miss any solutions is at this step, instead of writing just pi over 6, and it's 2 pi k on the end. Hi. Thank you. Abigail, for you. McDowell, sorry, Abigail Getson. I should have been more specific. Everybody's okay to this? Now we'll divide both sides by 2. When we do that, we get pi over 12 and pi plus k. We had to divide that piece by 2 also. Is everybody okay with that idea? Okay. So now we're going to pick some values of k and see if the result is still inside of our interval. And we'll keep picking larger and larger values of k until we get both answers outside of the desired interval. We're going to start with 0 here because our interval starts at 0 to 2 pi. So I know that I don't want to be subtracting anything from it, because if I subtract something from pi over 12 or 5 pi over 12, a multiple of pi anyways, it's going to be negative, and I don't care about it already. It's going to be too small. Gracie? Of course. So when k is 0, I get pi over 12 and 5 pi over 12. When k equals 1, I get pi over 12 plus pi. So that's 13. And that's still between 0 and 2 pi, right? So that one's good. If I do the same thing here, 5 pi over 12 plus pi, I get 17 pi over 12, which is still less than 2 pi, right? Okay. If k equals 2, I get pi over 12 plus 2 pi. So that's going to be big. That's bigger than 2 pi. And since the other one is a bigger answer, adding 2 pi to it will also be too big. Those are my solutions. Are those 4? Is everybody okay with that idea? Okay. Oh. Jason. So remember our the interval that we're solving over is 0 to 2 pi. This is bigger than 2 pi, right? 25 over 12 is 2 1/12. So it's too big. And this one, since we're adding 2 pi to 5/12, we're adding we're adding to a bigger number than we did in the previous one. We know that one's also going to be too big automatically. Is that okay? Yeah, no problem. Okay. This will be the last example we do today. We'll come back and do some more examples on this section, but I want to give you guys some time to just work on the homeworks and relax a little bit. So we'll do this example and then we'll stop, if that's okay with you guys. I don't hear any objections, so I'll assume that's okay. No, Mr. Kulik, I want to learn more math today. That math will still be there tomorrow. We'll get it, don't worry. So, same idea here as the previous ones. We'll start by square rooting both sides. because we generated a plus or minus, we're going to split that into two separate equations. And then we'll apply our in. Here I'm going to go ahead and rationalize the denominator because I recognize square root 2 over 2 is one of our unit circle values, so might as well. Similarly here, so when I go to my unit circle, I get pi 2 pi k, and I also get 7 pi over 4 plus 2 pi k. And here I get 3 pi over 4, and I get 5 pi over 4. And then I'll divide both sides by 3. So I get x is equal to pi over 12 plus 2/3. And I get x is equal to 7 pi over 12 plus 2/3 pi k. And then I get x is equal to, we'll just call that pi over 4 instead of 3 pi over 12, plus 2/3 pi k. And then we have 5 pi over 12 plus 2. So k equals 0. I get pi over 12. I get pi over 4. I get 7 pi over 12. And I get 5 pi over 12. Everybody's okay there? I know I don't have to go smaller because, again, I can't have a negative answer. And if I subtract 2/3 of a pi from any of these, I'm going to end up with a negative number, right? 2/3 is bigger than 7/12, so I know that I don't have to worry about that. So k equals 1. So I'm going to be adding 8/12 pi each time, right? 2/3 plus a 12th. When we make a common denominator, 2/3 is 8/12. So this one becomes 9 pi over 12. That's still our interval. This one becomes 8/12. Let's leave that as a 12. Easier to deal with that way. So that's 11 pi over 12, and that's going to be 15 pi over 12. We'll reduce all at the end, and then that'll be 13 pi over 12. And if k equals 2, I'm just going to be adding 8/12 to each of these answers I just got. So that's going to be 17 pi over 12, 19 pi over 12, 15 plus 8 is 23 pi over 12, and then 21 pi over 12. All of those are still less than 2 pi, right? So we're still okay. If I multiply, or if I do it again, so I'm adding another 8/12, that's going to be 25 pi over 12, and that's now too big, right? And notice that that was the smallest one of the previous 4. If that one's too big, all of the rest of these are got to be too big also. So this is my answers. We should just go back and reduce these when possible. That's probably easier to do all the reducing at the end rather than in the middle there, right? It was easier to keep everything with a 12th and not have a bunch of different denominators to worry about. I thought anyways. So at this point, we should be able to do from the homework set all of 15 through 46 and worksheet 2. I just want to do an example from this 15 through 46 because the directions are a little bit odd and we haven't done a specific example of what I mean by that or what I'm asking you to do on those. So I just want to do one of them as an example because it's quite easy once you do part A to do parts B, C, and D. A is the hard part. You don't really have to do much more to get the next parts. So I'm just going to do 15 here for us as an example. So for part A, we're solving on 0 to 2 pi. Part B, we're solving negative infinity to positive infinity. Part C, we're solving negative 2 pi to positive 2 pi. And part D, we're solving negative pi to positive 4 pi. So if I solve 15, I'm inverse of square root 3 over 2. If I go to my unit circle, 3 over 2 is positive as a y coordinate. So if I look that up, that's at pi over 3 and 2 pi over 3. So those are my two solutions for the first problem. There's my answer for part A, just like we did in all the examples, right? To get the answer for part B, all I'm going to do is part on. Everybody okay there? To do part C, if k equals 0, I get and 2 pi over 3. But those are both in between negative 2 pi and positive 2 pi, so those are good answers. So let's do negative. If I subtract 2 pi from this, I get negative 5 pi over 3, which is still bigger than negative 2 pi. And this one I'm going to get negative 4 pi over 3, which again is still bigger than negative 2 pi. If I try to do it again though, I'm going to get something too small, right? I'm going to get negative 11 pi over 3. So now I'll pick some values that are bigger to see if that works. So 2 pi plus pi over 3 becomes 7 pi over 3. And then this one becomes 8 pi over 3. And those are still big, or still smaller than, oh, no, those are too big, right? Those are bigger than 2 pi. So those are gone. So those are my 4 answers there. Everybody okay there? For part D, we want between negative pi and positive 4 pi. Well, these answers, that's too small, right? That's less than negative pi. That's less than negative pi. But these ones are still okay. These ones are less than 4 pi, so those answers are still okay. But if we tried adding another 2 pi, 13 pi over 3, that's less than 4 pi, right? No, that's bigger. That's too big, right? 4 pi is 12 pi over 3. So that's too big. Similarly, if we got 14 pi over 3, that would be too big. So this is k equals, what is it, 2? Would have been those ones that are too big. So you see that, like, once I have that first set of answers, I can immediately get my infinite set. And then I can just kind of test out values for k to figure out what lies in those other 2 intervals. Is that okay? I guess you guys will ask questions when you get to it and you have questions about stuff, right? You've been pretty good about that. We'll stop here. We have, I don't know, 15 or 20 minutes or something left in class. Take the rest of this time to start on something, whether it's this assignment or the worksheet 2 if you want to practice some more simplifying the trigonometric expressions, or finishing up the homework from 5-1 or whatever, you know. Do something, though. You know what I mean?